welcome to your background video for the Heat Up Reaction Lab. Thermodynamics can sound really difficult, but with a little planning, you can use it to make predictions or measurements. When we move to the laboratory and observe changes in thermodynamic parameters as a chemical reaction occurs, we call that thermochemistry. The chemical reaction causes that change. One important thermodynamic parameter is the enthalpy. The enthalpy is equal to the heat plus the work produced during a chemical change. If we control the experimental conditions, we can establish a system where the work term is essentially zero. Thus, if we determine the amount of heat, then we also know the enthalpy. Heat is a tricky and confusing term because we use that word outside of the laboratory in a way that is only somewhat related to science. The way you use the word at home causes you to interchange heat and temperature. They are related, but not the same. The relationship between heat and temperature is described by the equation Q is equal to the mass times the specific heat times the change in temperature. It should make sense to you that if you have more reactants, you get more heat. So, we can describe the amount of heat produced by the scale of the reaction. Remember that the amount in chemistry is best measured in terms of moles of the reaction. This statement becomes important to use because we can then relate the heat back to the enthalpy term. Once we talk about the how much, we also need to talk about limiting reagents. You'll be carrying out an acid-base reaction in a coffee cup calorimeter this week. The acid will be acetic acid and the base will be sodium hydroxide. This reaction is exothermic, which will cause the temperature of the system to increase as the reaction proceeds. The temperature change is related to the moles of reaction. And since we get 1 mole of water for every 1 mole of acid or base, we can refer to the moles of water produced. We will do our experiment in 2 parts. In exercise 1, we will know how much base we placed in the calorimeter. Carefully design the experiment so that the base is the limiting reagent. This allows us to know how many moles of products are produced. The volumes needed to do this aren't given, so you will have to figure out how to control the limiting reagent. In exercise 2, you will make the acid the limiting reagent. This is a little trickier because the concentration of the acid is not known accurately, but it is close to 1 molar. It is your task to determine this value more accurately. The progress of the reaction will be measured by a change in temperature of the reaction mixture. By the end of the lab, you should be able to calculate and report the enthalpy of the reaction and the concentration of an unknown acid. The goal of exercise 1 is to calculate the enthalpy of the reaction, so let's work backwards from there. Consider the units on enthalpy. They're kilojoules per mole. The moles will relate to the moles of product, water in this case, produced, and the kilojoules will relate to the heat released in that production. We will start with the kilojoule portion. We already stated that the equation for calculating heat is Q equals mc delta T. C represents the specific heat of water, 4.186 joules per gram degrees Celsius. This is a constant. M represents the mass of the solution. The solution here includes both the acetic acid and the sodium hydroxide. We will be measuring the volume of each solution in the lab instead of the mass because we don't want to put the solutions on the balance. It is okay to do this because the density of the solution is close enough to that of pure water. Think back to the physical properties experiment. What was the density of water? How would you move from the volume of a solution to the mass of the solution using the density? So now we've introduced the first 2 variables that we need data for, volume of both the acid and the base. Delta T represents the change in temperature, which you will measure using a thermometer, and you will keep this in degrees Celsius. Change in temperature is the 3rd and final data we will need to collect. Solving for Q will give us a value that is in joules. A simple conversion to kilojoules gives us the first piece of delta H. We're halfway to enthalpy already. Now let's tackle the moles of water portion. Remember when we said that we can relate the moles of product produced and the moles of reactant used using the net ionic equation? Well, here you go. The manual states that the base should be the limiting reagent for exercise 1. This is because we are using a base with a known concentration of 1 mole per liter. We can use this concentration to work towards moles as long as we have a known volume of base. Relate moles of base reacted to moles of water produced using the balance equation. You now have both the pieces you need to calculate the enthalpy. Perform the same steps for the remaining trials and calculate an average enthalpy. Compare this value to the known value for this reaction. As long as your TA finds your percent error and standard deviation acceptable, the math for exercise 1 is all done. You will collect the same data and use the same equations for exercises 1 and 2. And because the reactants are the same in both exercises, we can use the same net ionic equation. You will even perform the same technical steps for both sets of trials. The difference between the two exercises is that the limiting reagent is different. For exercise 1, the limiting reagent is the base. As we mentioned, this is because we have a known concentration of the base and we are able to easily measure a volume. This gives us a direct route from reactants to products, which allows us to calculate the enthalpy of the reaction, as you saw. The moles of water produced will be equal to the moles of base that reacted. For exercise 2, the goal is to calculate the concentration of the unknown acid in solution. In order to do this, we need to ensure that all of the moles of acid are being converted to moles of water. To do this, the acid must be the limiting reagent. This changes our calculations a little bit because without a known concentration of the acid, we can no longer move from moles of limiting reagent to moles of product. Luckily, the delta H calculated in exercise 1, which relates to the moles of water produced, is also valid for exercise 2 because it is the same reaction, only a different limiting reagent. Remember that your goal for exercise 2 is to determine the molarity of the acid. Reviewing the units for molarity, we can see that we will need to determine the moles of acid that reacted and the liters of acid solution that we used. Consider the average enthalpy value that you calculated in exercise 1. This is now the only item we have that has a mole component, so we will use this to work backwards towards moles of acid. To get moles by itself, you will need to first calculate Q. This is done the same way it was before. Now, think about how you can manipulate Q in kilojoules and delta H in kilojoules per mole to eliminate the kilojoules and solve for moles. How do the moles of water relate to the moles of acid? Solve this and you have the first piece of molarity. Now, all we're missing is the liter piece of the molarity. Look back at the data you collected. What piece of data that you collected could be used here? You got it? Good. This completes the background and calculation portion of this week's preparation. Remember that you will need to also view the technique video as well as reviewing the safety, background, and experimental portions of your laboratory manual. Good luck this week!